Now, with the radial basis function, we still have this computational challenge of keeping all the data and working with it. And of course, we have the option of discarding some of the data like we did in the nearest neighbor. But then let's look at one more approach that's known as the radial basis function with parameters, and using that build on something that's more useful and that can help us overcome certain issues with the RBF. All right, so here, let's quickly look at this very intuitive example. And also now we are beginning to derive radial basis functions that are known as like parametric radial basis functions. And in practice, I would say whenever we refer to RBF, it means the parametric one. And so that's why we're looking at that one. Let's look at some data, as I said. And in 2 dimensions, we have some data, let's say just 3 points, an easy example. And also we're looking at like the non-parametric one, so beginning with that, such that my R is like really small for this one, let's say like extremely small, 0.1 or 0.01, right? And of course, like we're assuming that this is utilizing the Gaussian kernel. And in a non-parametric RBF generally, with the Gaussian kernel, as your test point moves further away, right? So you will essentially be computing like minus like E minus S squared over 2 for each point. So the ratio of the distance from each of the points, like 1 and 2, for example, let's say this is 0.2, this is 1, 2, and this is 3, right? So this will go to 0. As you move further and further away from the data, the value that the test point takes is the one that's like nearest to these. And so you'll have like some kind of a flattening here and here. And then as you move like closer and closer, it is going to move in such a way that you literally have something like this. All right, and this is R small, so you can see that like the contribution of each point and the scale parameter have an effect on the way we're going to fit this. All right, now let's look at what happens when we increase R. Let's say when R is like really huge, then what happens? With the same points. Okay, and let's assume my R is 0.3, that's large enough, or 0.5. And of course, we have increased R, but like as you get further and further away, you will converge at one of these points. For example, here, as you start moving towards this, as you start moving towards the data, this point, because like R is large, it will start influencing it even when it like approaches near, right? So for example, it's going to go here, but then other points also have some impact. And with a larger R, as we saw earlier as well, this is going to go something like this. Of course, the pattern is similar, right? Because as you get further and further away, you'll converge to 0.3. Let's say this is 0.3. And the average of like all your points, or the weighted average, is just the value of 3, because it like becomes huge. This weight becomes huge because my R is huge. And so that's why, as compared to other weights. And so that's why we are getting this kind of a behavior. Okay, so this was the non-parametric RBF. And now just wanted to look at the behavior with respect to different R's. And now we're moving on to the parametric RBF. And we're going to do that by like starting to write the hypotheses for the non-parametric one, because we're going to build on that. So my g of x, if you remember, is the summation n is from 1 up to n alpha n x, and then the normalization alpha m x y n. Okay, if we look at like just this term here, this one here, this is like the weight of like data points with respect to x, or like the weighted average of target values. That's another way of like putting that. And so in my parametric RBF, I'm going to define it, or like redefine the same combination of values in a certain like in a way that's different from this, although it's derived from this. So let's look at that. So what we're looking at is the parametric RBF. All right. So what is that? As I said, I will just be like rewriting things, rearranging things, and we'll see why we're doing that. So my g of x, the equation that I just wrote here, I'm going to like, as I said, rearrange. I'm writing the summation, of course, And then how about we have this yn over the alpha m of x, and m is from 1 to m. And if you remember, this alpha n of x was some function phi that was essentially calculating the distance of these points. So bringing that back into picture. All right. So why are we bringing this particular term back into picture? That's because it's just a function, right? And this function is symmetric. That's what at least we said, that it is symmetric. And that's how we were trying to gauge the contribution of each point with respect to my x, right? So in other words, my bound of this function is like, or my bump or my curve is like centered at x, right? Because I'm trying to find the distance of every point with respect to x. Now, if I treat my x of n instead, so earlier I had my x as the center of the, like whatever symmetric function this was, and now I have xn. All right, you can say that this is a data point, but let's look at what's happening. So if we treat xn as a constant for, let's say, for the time being, then the bound can be considered to be like centered at xn. And it's convenient to view like this as a function of x instead. Why? Because this is, for example, let's say this was a Gaussian kernel. And mostly we're using, and in fact like 100% we're using symmetric functions. So the like by the argument of symmetry, we can do that. So let's look at like how it looks like. Let's say this was my x, and this was my data point xn. And now I said, and let's assume this is a Gaussian kernel. It's, oops, that's a bad drawing, of course. I would like to have somewhat, let me draw a line over there, and that's then easier to draw. Okay, slightly better, but not great. But let's like, we understand the idea, the intuition here. Okay, so now we're looking at the contribution of x on xn, this thing, to x, right? Which is equal to this, like this value of this curve, or the height of this curve essentially, right? Times some value. So basically this thing, this is in some ways telling me, like giving me some information about the curve, times this value. And this is now known as weights. So this is like the, now this is like, let's assume we are denoting it by Wn of x. Let's say these are some kind of weights. So in other words, what I'm trying to say is, if here this is, let's say again, my alpha n of x, which is kind of similar, like it's the same argument, except that I'm considering like this to be the constant and this to be the variable. That's it. And so essentially I'm like rearranging things here and saying that my g of x in this case is going to be some weight, because I'm trying to find the contribution of like x on xn, right? And so it is going to be some weight depending on the curve that's going to be there on that particular point, times whatever this function was giving me, right? And let me write down some to make it clear. So n equals 1 to n, and my function stays as it was. Now the only thing that I've assumed is, and this might look overwhelming initially, because now you might be thinking that now I have like this thing for every point, right? And so think about like the contribution of xn to the weighted average now is alpha n of x multiplied by my weights, wn of x, right? This is also like, and of course you would have already like figured what we are saying is, this is equivalent to raising the heights of the curve, or like at every point essentially, right? And those heights could be different, could depend on a lot of factors, but essentially we have like this bump for every data point. And so think of like placing another curve with some height at every point. So let me show you what I mean. Okay, so let's have like 2 points now. So this was my initial test point, but I have 2 of them. Let's say xm and xn. And because like the weights that we just like talked about will be like functions of these points. So let's say I have like some wm x, and so I have a curve here like a normal Gaussian curve, which like my drawing is not really justifying that, but you know what it looks like, right? And so let's say this is here W and N of X, and this is M. So essentially we'll have like curves on every point, placed curves, right? And instead of like um, a single height, because like initially I had just like one curve placed at the test point and then I was trying to get the contribution of other data points. I've like flipped it in the sense now I'm like checking the contribution of each of these curves on this like X. So then you'll say that the contribution of this curve is going to be something and then this curve. And yes, that's the idea. So we get the contribution of all of these and then add them up to get like my final g of X, right? Like another way of like viewing this is to imagine that each data point has a curve, and that's what we are saying, right? And essentially all those curves or all those bumps, they decay like in some ways over my test point, and you never know like how much they're going to decay, but that is going to contribute to the height at X. So that's going to contribute to the value that X takes essentially, and then we add them up. So this is like an approximation if you think about it. We don't um, a lot of like depending on my data, a lot of curves will overlap and things like that will happen. And so we essentially like chasing every curve for every point, right? So what we're doing is chasing curve. And of course, I'm going to talk about like how these weights come into picture, but let's say we know how to calculate them, right? So we are chasing curve for like every data point. And this is going to be just like an approximation. If we have lots of data points centered, let's say around this X, then it doesn't really make sense to calculate like each one of them. And so what we do in practice is like we do an approximation of that. So an approximation, what does that mean? Well, that means we don't necessarily need these heights to vary as much as we are doing right now. And so we can fix them beforehand, like as a constant. Let's fix like each one of them before doing anything else. And then depending on that, like take the sum of those and then go from there. So another way of like writing my g of X, and so I'm going to like update a little bit in the sense that, of course, each point will have its own, let me write it down, weight, but then it doesn't need to be necessarily a function of X in any ways. And so let me have it like as already fixed before we do anything. And so X minus Xn, this stays as it is. And here we are. So now this is my parametric RBF. Okay, so you can tell like where does the term like parametric comes in. We have like these parameters that need to be estimated or somehow evaluated. And before that, let's see what happens when these heights are fixed, because we're talking about like Wn not being a function of X anymore. And that's pretty intuitive, I would say. And let's see what that means. Again, we'll have like these multiple points, right? And so let's say like I have many points here, and I'm not even bothered about X at this point. I'm only bothered about my final hypotheses. And so let's assume there are, okay, this is like extremely bad drawing. Okay, forgive my drawing. And so the sum, like the final hypothesis is going to be the sum of these functions, and then height it's not directly dependent on test point, because like we don't want to chase heights for every data point, so we have fixed it. And so like we have these set of bumps because like every data point has a bump. And so the final hypothesis is somewhat like a sum of these. So it's going to look something like this. All right, so all of that is good. Now we understand what that means to like fixing the height. And so this is like for W1, W2, depending on like whatever points these are, X1, X2, and so on. Okay, so now the question arises, we've been talking about these bumps or these curves, and each one of them have like this parameter that's specifying its height. And so how do we find the heights? And so one way of doing that is, remember, like in our data, like if we have these X values, right, X3, X4, we also have the corresponding Y values with us. Okay, So the question arises, how does that help? So let's say I had already like some y values, and so this is like the two-dimensional space. And if I plot it here, maybe my y value was here, and this one was here, and this one was here, this one was here. Okay. So if I already had these y values, I can vary the size of these curves or these bumps so that I can like predict all y values correctly. In other words, I have four y values to predict, and by varying like these four heights, I can exactly get what I'm trying to get. So like my final hypothesis is going to be something that's like exactly getting these four values. So that could be one way of doing it. And of course, there is like a more principled approach of getting that, but that's how we can get it, right? That's how we can get the heights of my bumps. All right, let's quickly look at this example of how this happens. And we are looking at the same example that we started working with. And so let's look at the three data points that we had. And the R values, of course, were different. So this was like a small r, 0.1 or 0.01, I don't exactly remember. And let's see what happens when we're trying to apply this here. Okay, and so because r is 0.1, we are going to have like very narrow bumps because scale parameter is small. And this is like the illustration with very simple y values. And of course, if there are like two category of y values, you can have like bumps in different directions, could get complex. This is like a very simple illustration. So what happens in this case, the scale is really, and we're trying to chase like my y values, right? And so my curves are going to be very narrow because of my r. And this is exactly what my final hypothesis is going to look like, because I just like added these up and get something like this, right? So my final hypothesis is going to chase this essentially, and I'll get like exactly somewhat very similar to what we were trying to do. All right, what happens when r is large? Okay, let's say r is 0.3, so it's bigger, and the same 3 points. Now, because like the scale parameter is large, each curve is going to contribute more. So we'll have like some really big curves that are kind of obviously overlapping like this, right? And of course, when I'm trying to chase my final hypotheses, it's going to get something like this, the dotted part. And so of course it's smoother, the fit is going to be smoother. And in both cases, we are guaranteed to fit the data. So the danger of overfitting exists. Just remember that, because we have 3 points, 3 heights. So we are guaranteed to get the exact fit. All right. A little bit more about how to get these weights. We got the intuition of like how to get weights, but let's really look at the exact approach of how to get these weights in parametric RBF. And so let's begin with the equation again. G of x is n to n, and these were the weights, right? And then the phi has become like much cleaner, I would say, with everything on. Okay. Now, the things that we're trying to figure out are the heights of those curves that we get, right? And so these are my parameters. These are my parameters. And so that's why this is the parametric parameters. And what do we want? What do we want out of like this equation essentially? We want that, let's say there is a point x1, and so I should have something like gx1. Like in practice, this is what's going to happen, right? I'll have this equation and wn. I should be able to like find w when my phi x1, because this is like for that data point, minus xn over r is equal to y1, right? This is what I'm trying to get. And or like I'll have like g2 for point number 2 should be equal to y2, and then y2 is given to me. And so I'm trying to solve for those weights. And so eventually what I'm trying to do is I have like these n equations for each of the data points, right? And what I'm trying to do is n is from 1 up to n, wn phi xn minus xn over r equals yn. So I'm trying to get, because I already have the y values. So you think about like all these equations. What are these? So these are like n equations and n unknowns, right? So we can exactly like solve this system of equations. And so that's the first thing that we are observing is like looking at these equations. The other thing that we are observing is that the parameters in the equations are linear, right? And so the first thing that comes to your mind is this is a linear model. Of course, let's see how can this be a linear model. And let's use a feature transform that maps my x, my test point to each of the like points, each of the data points in, and let me show you what I'm trying to say. So I'm mapping this x to some z, which is like an n-dimensional feature transform. And notice this n is like the data, right? So feature transform. Okay, so what is this? Like, how do we get this z? So this z has like all these components, z1, z2, so on up to zn. And what is that each one of them looks like? So each one of these features is essentially this function phi calculated for one test point x minus x1 over r. And so the second one is going to be x minus x2 over r and so on. And zn, sorry, not zn here, phi x minus xn r, right? And you can think about like each of these components here and here, let's say any kth feature, is the kernel applied on x minus the distance to the kth point, right? So what does that tell you? The definition itself, what does it tell you? This tells us that these are nothing but similarity features. This is just measuring similarity. Okay, great. So if these are similarity features, and we have like n similarities to be computed, right? The only thing that's like different here, like a slight update, is that my features are defined by my data, right? So my features depend on my data, and I think you would have like already figured that it depend on the data. So that's a slight difference, and that's how we like formulated everything. So that's why my features depend on my data. Now, this is the feature vector for like all of the training points. That is like for data point x1, we compute the similarity feature, and for x2, we compute the other similarity feature, and so on. Okay, so we have like these z1, z2 up to zn, and of course, what we can do is we can collect all the values here into like a matrix. So let's do that, like write more formally, because we really like matrix notation. So I'm like making it really simple. So all we have is z1 transform, z2 transform, and so on, zn transform, right? And now we also have the target vector. We already have it. So y1, y2, yn. All right. So what exactly were we trying to solve when we began with all this from the beginning? I think like we lost track of that. So what we're trying to solve is to get this almost close to equal to y, whatever I'd like to call it. This here is my data matrix that I just got. And this here is my target vector. Just by looking at this equation, you can tell how we can solve it now, right? We can solve, this is nothing but our very famous and our favorite linear model, and this can be solved for regression, classification, or logistic regression. For example, for regression, and this is just like a repeat, we already know these things, but I'm still going to say I'm going to get wlin, right? And that's going to be z pseudo inverse y, which was, again, we have seen this so many times, inverse z transpose y. And z here, by the way, if you think about it, And just by looking at this here, you can tell it's an n by n matrix. It's a square matrix, which is good news. All right. And similar to the regression, classification can be, so again, I have the data matrix, I have the unknown weights, and so I can use pocket algorithm, PLA, and then improvise it and use the pocket algorithm to get the weights. And if I'm solving a logistic regression problem, I think it goes without saying that I can use the gradient descent because I have formulated my model. Okay, so this is my parametric RBF. And the good thing about the parametric RBF is that it reduces to the linear model with similarity features, right? A linear model with similarity based features or similarity features. And so we can easily like solve this, right? And okay, so although it's like guaranteed to fit the data, just like we saw with those three data points, but then like the thing that comes to my mind is that there are way too many parameters. And because it's like guaranteed to fit the data, it's the chances of overfitting are high. And so what we're going to do is we are going to figure that out, like how to deal with this overfitting issue. And can we do something like, can we improvise on this? And so we're going to look at that in the next video when we start talking about something that's known as the radial basis function networks.